All right, class, today I want to pick up where we left off yesterday on precipitation reactions and solubility product and solubility, molar solubility, all of those terms. Um, so what we're going to do today is one of the things that's interesting about precipitation reactions, we would like to be able to predict whether if we add two substances together, do we get a precipitate? And they could be dissimilar substances. So maybe I add lead 2 nitrate with sodium bromide, and I want to know, based on the concentrations of the lead 2 nitrate and based on the concentrations of the sodium bromide, if I add those together, do I get a large enough solubility product of the lead with the bromide for it to precipitate out? So that's what the focus is going to be for this lecture. It should be a short lecture compared to the other ones. And the other thing I really like about this lecture is I hope that once we get through today's lecture, you will integrate chapters 15, 16, and 17 together. 15 was the tools chapter. And I said you must know these tools in order to be successful in 16 and 17. 16 was the acid and base chapter. And then 17, buffers in the front end, titration in the middle, precipitation at the end. But you'll see throughout all of these, they have connectivity in that we're looking at a balanced chemical equation. We're looking at the products. And we are either neutralizing an acid or neutralizing a base, and then maybe we have a salt left over, and that's the conjugate, has the conjugate base of a weak acid or the conjugate acid of a weak base. And then here what we're looking at in precipitation is, do we exceed the solubility product so that the solution precipitates, or do we exceed the solubility of the substance? So that's what we got to look at. That's what the final focus is here. Is if we look at the slide here, we've seen this over and over again. If Q is less than K, then the reaction will shift to the right, and more solid will dissolve. So what we're looking at is if you let's see. Let me get my pen started here again. Oops. Let's try that again. For some reason the pen's acting up a little bit. All right, so what we're looking at is, like, again, silver chloride, solid. And then that becomes silver ions aqueous plus chloride ions aqueous. Okay, so if Q is less than the equilibrium constant, this reaction will go in the forward direction. And so this solid will dissolve, and so we have an unsaturated solution and no precipitation will occur. If Q is greater than the equilibrium constant, called the solubility product constant here, then the reaction is going to go in reverse in order to get Q up to KSP, and that means more solid's going to form, so you will see a precipitate. And if Q equals KSP, then you have you do have a saturated solution. So the way I want you to think of Q equal to KSP is that you have a container, you have the solution, and in the solution you're going to have, usually, doesn't have to be, but usually you have a pile of solid here. So some of it is dissolving into solution, and then some of it's going from solution back into the solid. So that's when. So if Q equals KSP, you do have a saturated solution, but no precipitation occurs because you're at the point of solubility. So remember, in a truly saturated solution, the point of saturation, the solution is homogeneous. There is no solid. You don't see a solid. So that's what I always say when we first introduce saturation and unsaturated. You can't tell the difference between saturated and unsaturated. At the saturation point, this solution still looks like an unsaturated solution. Now, when you add some more solute, if it sinks to the bottom and you stir it up and it doesn't go away, then you know you were at a saturated point. But if you add more and then this dissolves, then you are still an unsaturated solution. So just keep that in mind, that you can't tell the difference between saturated and unsaturated until after you add some more and see what goes on. Or mathematically, if you haven't reached the solubility of the substance, then it's unsaturated. Right at solubility limit, it's a saturated solution, and beyond it's a saturated solution. So just keep that in mind. I think that's an important point there. Now, a supersaturated, that's the one that throws students the most too. It's when you have Q greater than K, all right? And it should precipitate out, but it doesn't. So here's what it looks like. I'll show you on this next slide. I'll show you what a and you should look this up. Just Google YouTube videos or go to YouTube and Google examples of supersaturated solution, because I think it's really cool to watch. But here it is. This solution, if you look at it right now, it looks like an unsaturated solution, or it could be a saturated solution. We can't tell. It's all clear. It's colorless. And then they have one little crystal up here, one little crystal, and they drop the one crystal into the solution, and bam, all of this forms here. So that tells me that this is a supersaturated solution, because if it was just saturated, the one crystal would sink to the bottom. You stir it around, it doesn't look like it dissolves. But you add one little crystal and you get all of these crystals, that tells me it was a supersaturated solution. So usually what happens when Q is greater than KSP, as soon as you add one drop, you start to see a precipitation reaction. Or if you add multiple drops, in this case probably. But here, when you get one crystal in or one drop in and you get all of these crystals formed, that tells you that was a supersaturated solution. So what is a supersaturated? You have the conditions of Q being greater than KSP, but the solute stays dissolved in the solution, and then you need a little bit of a oomph to cause it to precipitate out. So what are the ways to oomph it? You add a seed crystal, or you can take a glass stirring rod and kind of scratch the inside surface of the glass, and it'll cause a crystal to form there. Then all of a sudden it'll precipitate out. It's kind of a neat thing. I would encourage you to look at a couple of videos on YouTube to see what that looks like. But the bottom line is, this is the theoretical part, that Q is greater than KSP. You don't have a precipitate. If you had a precipitate, then you know it would be saturated. If that's generally what happens. But if you don't have a precipitate and Q is greater than KSP, then you have a supersaturated solution. All right, so this is the problem I'm talking about. This is a very important problem. We use this in a lab a lot, and that is you have two substances. In this case, you have a lead 2 nitrate. And again, you should know that this substance is water soluble. And you go, I don't know that this substance is water soluble. Well, that means you need to go back and memorize those solubility rules. It's that important. So lead 2 nitrate is water soluble. And we're going to combine that with sodium bromide, which is also water soluble. All group 1A compounds are water soluble. And I should put an AQ, but I'm running out of room, so I'm not going to do it. All right. So when we mix these two things together, we get lead 2 bromide. And that is a solid. It precipitates out because the solubility rules say all chlorides, bromides, and iodides are water soluble except with lead, mercury, or silver. So that precipitates out, and then we have the salt, sodium nitrate. And we know that that's water soluble, so we'll put an AQ to represent that. So the question is, this concentration is 0.01550 molar, and the sodium bromide is 0.00350 molar. And the question is, will the concentration of the lead and the bromide exceed the solubility product for lead to bromide? That's what we're trying to do here. So we have two separate substances that are water soluble. They're in two separate test tubes. We pour them into the beaker, and what we want to know before we actually see this reaction is we want to be able to predict whether it will precipitate out or not. All right? So what do you think? Well, it's not as easy as just looking at it and coming up with an answer. So let me erase this so we can see other components. So let me just erase all of that. But that's the process right there. Okay. So let's move to the next part of it. So here's what you got to know. You know that sodium nitrate is soluble in water. Here's the solubility rules. This is in Chapter 8. You need to memorize that. I can't stress that enough. You've got to memorize the solubility rules. Especially, I just memorize this part, and then I assume everything else is insoluble. Now you say, what about sodium hydroxide? Well, we know, according to the rule, all sodium compounds are water soluble, so that's why we don't worry about that. So that's why they talk about exceptions over here. But just memorize the top part. It's not that hard. Get you some flashcards. Put on one side one rule and the other side the exceptions or something like that, and go through them. But you have to know that. It makes it much easier. All right, the solubility product of lead to bromide is 4.67 times 10 to the negative 6. Nope, I don't expect you to memorize that. That's given in a table or given into the problem. All right, what I do expect you to be able to do is, based on the equation that we wrote, lead to nitrate reacts with sodium. What did I do there? I didn't do that right. Yeah, reacts with sodium bromide, and then forms the solid lead to bromide. Yeah. Plus sodium nitrate, which we're not really interested in. So there's my balanced chemical equation. So we're not interested in that. That's a spectator ion. So what I do expect you to know is that if we look at the solubility of lead to bromide, that is equal to yields the lead 2 ion plus the 2 bromide ions. That you can write the solubility product for that expression. So KSP for that equals the lead to positive concentration times the bromide ion concentration raised to the second power. So again, that's from chapter 15, right? Take any chemical equation and write the equilibrium expression. This one's called a solubility product expression. So I do expect you to be able to do that. That should be easy. So what we know is, we know what the KSP is. KSP is here. We're going to plug that in there. We can figure out what the lead concentration is, the lead 2 ion. So up here, this is the concentration of the substance, and it's 1 to 1. So that is the concentration of the lead, 0.0150. All right. And then we know that the sodium bromide, the concentration is 0.00350. So you may be saying, well, don't we multiply that by 2? No, because we're not starting with this lead to bromide and making this. We have this concentration of the bromide and we have this concentration of the lead, 2 positive ion. Now, we do need to square this. I'll go with that. But now what we need to find out is when we calculate this, that's going to be Q, because we don't, this is initial concentrations, not equilibrium. So if Q is less than KSP, then the reaction is going to go this direction and we don't form a precipitate. If Q is greater than KSP, then the reaction goes in reverse and we are going to form the precipitate. So that is the process in determining when we add 2 dissimilar substances, mix them together and they form a precipitate. Ultimately, what we have to do here is calculate Q, and then based on Q, we're going to say a precipitate forms or it doesn't form. All right, let's see. I'm going to click this. It may get a little messy here, but so here it is. Just like we said, this should be squared. It's not raised to the second power there. Right? There's a little typo right there. So we should get 1.84 times 10 to the negative 7. Let me just make sure that's right since there's a typo there. So we take 0.0150 and then we multiply that by 0.0035 squared. And yeah, we get that number. So we look at this value, which is Q, and Q is less than KSP. Here's our KSP up here. Since Q is less than KSP, no precipitate forms. So that's the power of this calculation, is before you added a certain concentration of lead-2 nitrate and a certain concentration of sodium bromide into the same reaction container, same beaker, you're able to predict whether you think a precipitate will form or not. So Q being less than KSP, no precipitates form. Now, if Q is greater than KSP, you can't for sure say a precipitate will form. You either have you can say that you either have a saturated or a supersaturated solution. But again, sometimes you add things together and Q can be larger than KSP, and if not, we just don't have that spark for it to precipitate out, and therefore you'd have a supersaturated solution. All right, so let's have you guys try that one. All right, so hit pause, try to work this one out, and see what you get for an answer, and then I'll work it out here, and then we'll see what's going on. So same thing. Same thing. Lead, 2 nitrate, aqueous. I got more room here. All right, and we're going to react that with 2 moles of sodium bromide, aqueous, and that's going to form lead 2 bromide, solid, plus 2 moles of sodium nitrate. So that's my first equation. Second equation is solubility equation. Lead 2 bromide solid yields lead 2 positive ions aqueous and 2 bromide ions aqueous. And so the KSP for this, the solubility product, is equal to the lead 2 positive concentration times the bromide ion concentration raised to the second power. All right, so we know that this is 0.0600 molar. Again, 1 to 1, 1 to 1. And the bromide is this number. So it's again 1 to 1 in the sodium bromide. All right. So let's calculate that out, see what we get for an answer. So we have 0.06 times 0.0158 squared, 1.49 times 10 to the negative 5th. So this is Q. This is not KSP. Q is 1.49, or let's just say 50, times 10 to the negative 5th. All right. So then we compare that to the KSP. So let's flip back a slide. And it's 4.67 times 10 to the negative fifth. So Q is greater than K. And because Q is greater than K, this reaction is going to go this way, and the precipitate is going to form. All right. I like these problems. It's kind of neat. I mean, you're predicting something before you actually do it in the lab, and you know, that's why we do all this. It's so that we can predict things that happen experimentally, and we expect that when we do these calculations based on the concepts, we should get these answers. Now, again, could be surprising. You could add these together and you don't see a precipitate forms. You go, well, I should definitely get a precipitate. Well, you probably have a supersaturated solution then. So you go, why would I ever use this in real life? Well, the reason why you would use this is you want to separate one substance from a mixture. Like you want to separate the lead to bromide from the rest. So it's kind of like it's a purification process. Right now you've got the lead to bromide separated from the rest of the solution. You could pour that through some filter paper. The lead to bromide would stick to the filter paper. The rest of the ions and the solvent would go through the filter paper. And you could actually do successive ones of that to purify the substance. So that's one of the reasons why you want to use solubility products and solubilities to selectively precipitate what you're interested in isolating. All right, so here's a good problem. All right, so here it says the magnesium and calcium ions present in seawater are these concentrations and can be separated by selective precipitation with the potassium hydroxide. All right, so what minimum hydroxide ion concentration triggers the precipitation of the magnesium 2 positive ion? All right, so my first question to you is what precipitate are we talking about? And which one of these substances is going to have the largest KSP? All right, you could hit pause, think about it. All right, so what we're looking at is magnesium hydroxide precipitate. And we're looking at calcium hydroxide precipitate. Now, we're trying to precipitate out the magnesium. So we know that we want this to have the lowest KSP. We don't want it to form the ions. We want it to stay as the solid. So magnesium should have the lowest KSP. All right. So let's look at the problem. And I probably need to erase. All right. So we got to calculate Q for magnesium hydroxide. So magnesium hydroxide dissociates, I should say, into magnesium 2 positive ions and 2 hydroxide ions. Here's my expression. I plug in the initial concentration of the magnesium ion. Where did I get that? Right here it is. Okay. And then the hydroxide ion concentration is what I got to solve for. All right. So when Q equals KSP, the KSP for magnesium hydroxide is this. I don't know what the hydroxide ion the minimum hydroxide concentration for saturation is. That's what I need to find out. So I'm solving for the hydroxide ion, and I get 1.9 times 10 to the negative 6 molar. So to reach the saturation point, I have to add this amount of hydroxide ion to react with the magnesium ion to reach the solubility limit of magnesium hydroxide. So if I actually want to see precipitation, I have to exceed this amount. So this is the equilibrium amount. This is the equilibrium amount, but I need to exceed that amount in order for the precipitate to be formed. So what we've done here, we have precipitated out the magnesium ion from the seawater, and the calcium ion still remains in the seawater. It's neat stuff, neat stuff. Now you've separated out the magnesium. Good problem. All right, and you could do this one. Should be pretty much the same process as that. So the last topic of chapter 17 that we're going to cover is complex ion formation. I'm not going to ask you to do this mathematically, but we are going to talk about it conceptually. And the reason why I want to talk about this is that I see this happen in the lab a lot, where students are combining something like ammonia with silver ion, and they generally what's happened is they've added too much ammonia to the silver ion solution. And so with just a little bit of ammonia first, ammonia, when it reacts with water, forms the hydroxide ion, and the hydroxide ion can react with the silver and form a silver hydroxide precipitate. But if you add too many drops of ammonia, then the ammonia complexes or bonds with the silver ion, and we form a complex ion. And that complex ion is usually soluble in water. And so you have a student come up to you in lab and say, hey, I've followed directions and I've added the ammonia and I'm not seeing anything. And generally what has happened there is they've added too much ammonia and it's formed a complex. So I want to talk about complex ions and how they operate. So here we see silver ion reacts with water and forms a silver water complex. And that silver water complex is soluble in water. So we call these water molecules attached to the metal ion a ligand. So just know the term ligand. Ligand is a substance, ion or molecule attached to that metal ion. So ligands can be substituted. So here we have the silver water complex, and we add ammonia, and now the ammonia does a single replacement reaction with the water, and now we have a silver ammonium complex, and then the water's been released. So because water is a pure liquid, its concentration does not change appreciably over the course of the reaction. We remove that from the balanced chemical equation here. And we know water is present because it says aqueous. So if we write the expression for this, this is called a complex ion formation expression. So we have our final equilibrium constant, Kf, formation constant. So the formation constant, much like a solubility product constant, if Q exceeds K, then we're going to form the, if Q exceeds K, the reaction goes in reverse. If Q is greater than K, if Q is less than K, the reaction goes in the forward direction. Same thing. So here are the formation constants of many complex ions. So there's the ammonia. And you can see right off the bat, this substance wants to form, right? Look at that. Look how big the the formation constant is. So I'm not asking you to do this calculation. We're going to skip the calculation. You can look over it if you want to look at it and try to understand it. It's good practice for extending beyond solubility product. And it'll show you mathematically what's happening. So this is always a cool one too, because when copper reacts with ammonia, you get this regal blue solution, and that's why they're probably showing this particular example. And again, it's a nice table, it's a calculation. I just don't think it's worth doing this one as well, especially since lab has been canceled or delayed or whatever, or you're not going to get to this, and that's why you would really show this. This is something that's better to see in the lab and explain why it's happening in the lab. Okay, but what I do want you to understand is this slide. Conceptually, I do want you to understand complex ion formation. So we have a precipitate, and that is silver chloride. And so you've mixed something in the lab together, and you've gotten the precipitate. Oops, let's go back. Pen didn't take. So here's your precipitate, and that's what you expect. Oh, I'm supposed to get a precipitate, and then you can, when you do this in the lab, now what you can do is you could pour this through filter paper, and you would collect the silver chloride, and hopefully most of this has been, you force the reaction to go this direction, and you mostly have silver chloride, and then the rest of your ions, maybe you've got some other impurities, as we would call them. Like maybe you have some lead, or maybe you have some iron or something like that. That goes through the filter paper, and you've collected the silver chloride. But what happens is maybe you're adding silver or ammonia to the solution to make a hydroxide, because ammonia reacts with water and forms a hydroxide ion, and you added too much ammonia. And so if you add too much ammonia, the silver ion is going to react with the ammonia and form this silver ammonium complex, which is aqueous. So now you don't have the precipitate. In fact, you see the precipitate, if you observe this, you might have had a solid here, and then all of a sudden the solid disappears when you add ammonia. So the ammonium complex goes through the filter paper, and you don't collect the silver. And this is going to happen because look at that formation. Formation's huge. So yes, this reaction wants to go in this direction, but this reaction wants to go in this direction. So as the silver reacts with the ammonia, this reaction is going to happen, right? It's more probable. It doesn't talk about the speed or anything like that, but it does. It's more probable because this has such a high formation constant versus the solubility of this. So once this starts being removed, this reaction has to shift to the right to make up for the loss of that. Le Chatelier's principle again. So we're at equilibrium. You remove the silver ion. Seesaw gets like the balance gets like this, so the reaction has to shift to the right to make up for that loss. Why are we losing it? Because the ammonia is complexing with the silver. So that's what I want you to know about complex ion formation. A lot of times you're looking for a precipitate. You're looking for this. Here it is. Here's the precipitate. But because you've introduced ammonia, and maybe too much ammonia, you form the ammonium complex, and that binds the silver, and so then more of this has to dissolve to make up for that loss of silver ion. Neat stuff. It's a chemistry in itself, and it can be used to help also separate different ions. So usually we think of it as a problem because you try to collect the silver chloride, and all of a sudden your silver chloride is just dissolving away because you added too much ammonia. All right, that's where we'll stop chapter 17 in this lecture. We have a test coming up, If you have questions, make sure you email me, and I'll help set up the exam for next week. So just look at it all. Look at 15, 16, and 17. Try to integrate it all together. Yes, the test is only over chapter 17 this time, but if you don't understand acid and base salts, if you don't understand conjugate base, conjugate acid, ice tables, Q, the reaction quotient, and how we use that to determine which way the reaction is going to go, that's some of the material in 15 and 16 that you need to go back and review. For precipitation reactions, I think the most important thing, outside of what's in the chapter, is you know those solubility rules. Because if you don't know the solubility rules, or you don't know the charges on your polyatomic ions, then you're not going to get a correct balance equation. If you don't get the correct balance equation, you're not going to get the correct equilibrium expression or solubility product expression. So it is a kind of an integration chapter, and if you need help, email me what you need help on. I can either make a video or comment. Post stuff on the discussion board if you're kind of asking the question like you would be asking in class. And if you're stuck with the calculations or a particular concept, then try the Thinking Storm online tutoring. I think that should be helpful given the situation.